One of the very specific uses of the definition of work is to couple it with the idea of what friction is and then examine what the work due to friction would all be about. So the definition we have then is that work is equal to the applied force dotted into the displacement like this. And so what we'll do in this case here is, in particular, we'll say, well, what if the force we're dealing with is friction? What if it's the frictional force, including the vector direction of friction there? Well, what we know about friction then in terms of the direction here is it always opposes motion. And by motion here, we can always sort of pick off the motion by v, but remember that delta x is sort of in there too, but never fear, because you know that delta x here is equal to v times delta t. So as long as that v is in the same direction as delta x and your time step is kind of small here, v and delta x will be in the same direction. So friction always opposes motion. That means it's opposing both the velocity, instantaneous velocity of the object traveling in, and the displacement which is about to cover. So that's the case that we'll consider here. So if it always opposes motion like that, then what you have is a case like this. You have a block like this here that's, say, moving this way with some speed v. Now, if you let a little bit of time go by, like a little bit later in the future, the block will be over here, maybe still traveling with a speed v, whatever the case may be, but it's undergone some displacement now. Here is your delta x that you need for your work function. And you can look in the video on the car to see how delta x was there, but it's just the distance over which the object just moved. Now, if the surface under the block here is really rough, or we're purposely stressing that there's some friction here, so there's some mu, there's a coefficient of friction in there, then what will happen is as the object moves over the friction, as it's moving to the right, there's always going to be a frictional force on it to the left, this way. There'll be a frictional force that way. And even over here, as it still slides, there'll be a frictional force that way, something like that. So again, this is the idea that there's a force on the object which is opposing its motion. And in this case here, if you look very carefully at this, the angle between the force and the displacement here is 180 degrees. Angle between the force and displacement, 180 degrees. Now I know this is v here, but again, the displacement is always to the right also, so nothing changes there. The angle is still 180 degrees. Now if you look at the video on work again there, remember that work involves the force, the magnitude of force, times the displacement times the cosine of the angle. Now if the cosine of the angle is 180 degrees, this is going to be -1. So the work we'll get due to friction then is going to be minus the frictional force times the displacement. And this is the big specific result here, insofar as it applies to friction there, is that the work that friction does is always negative. That's the big result right here. The work due to friction is always less than 0. What do you conclude from something like that? What you conclude from that is that friction always removes energy from a system. Always. And that's the nature of the game. Friction always is sort of the drag on all motion. You try to move right, friction tries to pull you to the left. You try to move left, friction tries to pull you to the right. And we even see in our definition of work here that the work due to friction is always going to be less than 0, because friction is always trying to pull energy out of a system here. If you look up here at this particular figure here, as the object slides across the ground here, what's happening? Well, we'll draw a big red arrow like this to indicate energy flow. We just have a constant stream of energy flowing out of the system into the ground. Yeah, that's right. So the energy that the block has is sliding over the ground is leaking into the ground, actually heating up the ground a little bit, but it's energy that's lost forever. And you know this happens. If you push your textbook across a table, it eventually slows down and stops. Now, it had kinetic energy when you originally pushed it. Where did the kinetic energy go? Went into the table because of the negative work done that friction has done on the object as it slides. So the work due to friction is always negative, and this is as friction ties with energy. Friction always removes energy from a system, slowing it down, sucking its kinetic energy away. So let's just look at a quick example of what might happen or how this might work here. Suppose you had a nice frictionless surface like this, then suddenly it got really rough, and maybe it was frictionless again, something like that. And suppose you had a block here on this side that was going this way with some speed v, and it had a mass m, the usual parameters. And say the frictional patch here was a delta x long until it hit no friction again. So here mu is equal to some number here, and these two sections are frictionless. So the question is, when the block makes it onto this surface, and we'll assume that it has the kinetic energy that can make it over here, what is the speed over here? We'll call the speed over here v naught, and the speed over there v. So what speed does it have when it makes it all the way over to the right here? Well, you can use energy considerations to figure this out, because you know when the block hits this surface right here, what's going to happen? Friction, there's going to be a frictional force which is going to pop up on it, because that's what friction does. It always opposes motion as the block tries to move this way. And again, big red arrow of energy just escaping out of the block into the ground. So what you'd expect then for sure over here is that V is definitely going to be less than V naught. In other words, when the block passes over the friction and makes it out, this speed is going to be less than the original speed it had when it entered the friction surface there. So the way you could actually figure something like that out is you could do something like, well, use the work. You know the work due to friction here is minus the frictional force times that displacement. In other words, the delta x, how long was the frictional patch? And we know that the change in kinetic energy, delta Ke then, is the work done. So 1/2 mv squared minus 1/2 mv naught squared. There's your change in kinetic energy right there. That'll be minus the frictional force times delta x. And so, for instance, if you know how fast the block is moving initially over there, this is how fast it'll be moving when it makes it over the frictional patch, and this is the energy lost here, or taken from the system because of friction. Now you have to go ahead and find the force of friction here, and of course you can do that because you might know or remember that the frictional force is equal to mu times the normal force. There's still going to be a delta x in there, and the mu here is a coefficient of friction, of course. Now you have to come up with a normal force. You've been cautioned over and over again about how to find the normal force, but if you were careful in doing this case, you get the normal force is just mg, the weight of the block, times delta x. So in other words, you can copy this down here, but that change in kinetic energy of the block is going to be negative, less than 0. The block will lose energy. This is the amount it's going to lose. The coefficient times its weight times the delta x. That'll be the change in kinetic energy. All the energy got lost due to friction in the ground. That's just another, not another, but it is a very specific use of the work, in this case due to friction, always a negative quantity.